Okay, so what is telescope? So telescope helps us to see the distant object like moon, planets, stars, etc., etc. clearly. So if you want to see the distant object means the object which are very far from us, known as the distant
Yes, sir.
object. So, like you have heard the name of James Webb Telescope. Now, new telescope is introduced, known as the James Webb Telescope. Earlier, we
Yes, sir.
have Hubble. Earlier, we have NASA have the uh, which telescope? James Hubble Telescope. Now they
Yes.
have improvised. They have improvised, and they have the uh, James Webb Telescope. So, what is the use of that telescope? Basically, there was one image on internet of the galaxy and planets. Basically, that image is taken with the help of that telescope. So, the use of the telescope is to see the distant object clearly, like stars, moon, planets, and all that.
Yes,
Okay,
sir.
and in that image there are certain stars also. The image that is taken by the James Webb Telescope. In that image, you can see, if you will find that image on internet, you can see there are the images of stars and planets, and those stars and planets are very very far from us, very very far from us. Okay,
Yes, sir.
and with the help of the telescope, that image can be taken clearly. So basically, that is the use of the telescope. So what is telescope? Telescope helps us to see the distant object like moon, planets, stars, etc. clearly. Now,
Yes, sir.
there is one more thing: visual angle. This visual angle I discussed in the uh, microscope also. Again, I am discussing what is visual angle. Suppose this is your eye, and this part of the eye is retina. So I told you retina is basically a screen on which the image is formed of the object, and retina have the light sensitive cells also, rods and cones, and due to which the electrical signals are generated, and those electrical signals are sent to the uh, brain through the optic nerve. That is why we are able to see the image of object. Okay, by the way, so this is the eye, and this is the object, and this object is subtending the angle theta. So basically, this angle, the object subtending at eye, is the visual angle. Okay, the angle subtended by the
Yes,
object
sir.
at eye is the visual angle. So you can write here the angle
Yes, sir.
subtended by the object. Okay, so it is, just a minute. Visual angle is the angle subtended by object at eye. So you can see here, this is the eye, and this is the angle subtended by the object at eye. Okay, so this angle is theta. So in the same way, this angle will also be theta. So more will be the angle theta, more bigger will be the image. Okay, more will be the angle theta, more bigger will be the image. More value of theta, bigger is the image. Okay, so this is known. This is the visual angle. Now we'll discuss the magnifying power of telescope. Magnifying power of telescope is equal to visual angle found by the final image, and divided by the visual angle found by the object. Visual angle found by the final image divided by the visual angle found by the object. Okay, so before studying the telescope, we should know what is the magnifying power of the telescope, because all these things we will use. This thing I will also use, this thing I will also use when we will discuss telescope. So basically, telescopes are of two types. One is the refracting telescope, another is the reflecting telescope. So mostly we will discuss the refracting telescope, and after that we will discuss the reflecting telescope also. Uh, so first, please write down this properly, and you should know what is the visual angle, and you should know what is the magnifying power of the telescope. And after this,
Yes,
we
sir.
will discuss the telescope. What is the telescope? Okay, refracting telescope we will discuss. First, write down this, then we will discuss.
Second scroll down.
Okay.
Done, sir.
Okay. So now we will discuss the working of the refracting telescope. Working of the refracting telescope. What is the refracting telescope? Basically, in the refracting telescope, there is one objective lens. There is one objective lens, and that objective lens is
Yes,
of
sir.
very
Done,
large.
sir.
Huh.
Sir, we did this, right?
No, no. Actually, we have not done this. Actually, we have done
Oh,
simple one.
yeah, that was compound microscope. Yeah.
Compound microscope. You can see here. Actually, I was telling. In compound microscope also there is one objective lens, there is one eyepiece lens. But in compound microscope, the objective lens is small in
Okay,
size,
okay.
smaller in size as compared to the eyepiece lens. Okay, this is different and that is different. So in case of the telescope, refracting telescope, now you have the objective lens and you have eyepiece lens. But in this object compound micro refracting telescope, objective lens is bigger. Okay.
Okay.
But
Yes, sir.
in case of the compound microscope, objective lens is small, eyepiece lens is large. But here our objective lens is large, and I will tell you the reason also why this objective lens is large. And this is the eyepiece lens. This is the eyepiece lens, and both are the convex lens. Okay, why we made the objective lens large? Uh, Objective lens is of large aperture, means large, and large focal length, so that it can collect more light from the distant object. Actually, we want to see the distant object light like stars, like uh, moon, all that. So for getting the clear image, okay, for getting the clear image, uh, we should have we should have more amount of light from that object that we want to see. Okay, and we know that
Yes, sir.
the object that we want to see, like moon, like stars, are very very far from us. So we will consider those objects at infinity, and we know that if an object is infinity, if an object is at infinity, then rays from that object are parallel. Now these are the
Yes,
parallel
sir.
rays. Okay, these are the parallel rays from the object that we want to see. Okay, these are the parallel rays. So we can write here parallel rays from object. So these are parallel rays from distant object. Distant means the object which is very large, at a very large distance. So distant object. Okay, now see. So these are the parallel rays. Okay, from the distant object, these are the parallel rays,
Yes,
and
sir.
this is the objective lens, and this objective lens is of large focal length. Why we have made this objective lens is of large focal length? Because we want more light should come. Okay, because if the objective lens will be of
Yes,
large
sir.
aperture, it can gather more light, or it can cover more
Yes, sir.
light, or it can collect more light. So now we are just showing two rays. Okay, there will be more number of rays actually, but we are only showing two rays because we want to make the ray diagram. So these are the
Okay.
rays, these are the parallel rays. So these are the parallel rays, and first ray is like this, passing from the optical, this is the optical center of this lens, and it will pass straight. Another ray is like this, after refraction from the lens, both the rays are meeting here. So means here this objective lens will form the image of distant object. The distant object means like moon and the planets. of those objects, the image will form at this point here. Okay, so we can say that here is the image. Here is the image. This is the image of the
Yes,
distant
sir.
object. Okay, so this is the image of the distant object. I'm supposing this as A dash and this is B dash. Now we know that this is the convex lens and these are the parallel rays. And where the parallel rays meet? Parallel rays always meet at focal plane. We know
Yes,
that
sir.
parallel
Yes.
rays always meet at focal
Focal
plane.
plane.
Okay, if this point is lying on the focal plane, it means that this will be the focus of the objective lens.
Yes, sir.
Will be the focus of the objective lens. Focus of the objective lens. So basically, these rays are meeting at the focal plane. Okay, these rays are meeting at the focal plane, and this is the image of the distant object. Now here there will be a work of the eyepiece lens. Now this is the image found by the objective lens. Now this image, okay, this image will be worked as a virtual object for the eyepiece lens. Okay, earlier also
Yes,
we
sir.
have done this in case of the compound microscope. Okay, in case of the compound microscope. Now this image will work as an object for this eyepiece lens. Okay, now for this eyepiece lens, uh, and this compound microscope is adjusted in such a way so that this image is in between the optical center of the eyepiece lens and the focus of the eyepiece lens. Okay, this is the focus of the eyepiece lens. Here is the focus of the eyepiece lens. Understand now what I'm saying?
Yes, sir.
This image
Yes,
is
sir. Got
this image is lying in between the optical center and the eyepiece
focus.
and the focus of the eyepiece lens. Okay, now this is the case. You can see here. This is the this case. When the object is in between the focus and the when the
Optical
object
center.
then where the image will form on the same side and
Yes, sir.
it will be larger in size.
Larger in
This
size.
actually this will be the case there. Okay, this will be the case there. So here this object is lying between the focus and the optical center of the eyepiece lens. Now we will draw the ray diagram for this. Okay. Now this is basically the image with respect to the objective lens, but when we are talking about the eyepiece lens, with respect to the eyepiece lens, this image will work as a virtual object. Okay, now we
Yes,
will
sir.
draw the ray diagram. First ray from the object is parallel to the principal axis like this, and if a ray of light is parallel to the principal axis after passing from the lens, it will pass from the focus, second focus. Okay, like this.
Yes, sir.
It can be like this. Okay, this is the first case. Now, second ray from this is passing from the second ray from this object is passing from the optical center and is passing straight. If a ray of light is passing from the optical center, so it will pass straight now, always.
Yes, sir. Yes,
Okay.
sir.
Okay. Now, here you can see these rays are the diverging rays. These rays are the diverging rays. Diverging rays. And diverging rays will never meet in actual. In actual,
Yes, sir.
diverging rays will never meet. Okay. So what we will do, we will produce these diverging rays in the backward direction to form the image. Okay, we will produce now these diverging rays in the backward direction. So I'm producing
Yes, sir.
these diverging rays in the backward direction. Somewhere here, these diverging rays will meet. So we will make these produce diverging rays with the dotted line. somewhere here the final image will form. So here this image is forming, final image.
Yes,
This is
sir.
the final image. This is the final image of the distant object. Okay, this is the final image of the distant object. Okay, so basically what is happening, you can see first is the objective lens, and objective
Yes,
lens is
sir.
bigger in case of telescope. In case of telescope, the objective lens is bigger as compared to the eyepiece lens. Why the objective lens is bigger? Because to collect the more light, the lens should be bigger. So parallel rays are coming from the distant object, and this lens is the objective lens, and this objective lens is forming the image here, and this image is working as a virtual object for eyepiece lens, and this eyepiece lens is forming the image here, and this is the final image. Okay, now we will mark the distances. We will mark distances. So if talking about this distance, the distance between the optical center and FO, this distance will be the focal length of the objective lens. And talking about this distance, the distance between this object and this optical center will be the object distance for the eyepiece lens. Okay, because this is the
Yes, sir.
object for the eyepiece lens, so this distance means this distance, or you can say this distance will be the object distance for the eyepiece lens. Okay, after that we will calculate the magnifying power. Now we will calculate the magnifying power of the uh, telescope. Now what is the magnifying power for the telescope? You can say visual angle formed by the final image. Magnifying power of the telescope, see, visual angle formed by the final image, that is beta, divided by
Yes,
visual
sir.
angle formed by the object.
Alpha.
Okay, alpha. Okay, so visual angle formed by the final image, this is the final image, and this angle means this angle will be beta.
Yes, sir.
Visual angle, this will be the visual angle formed by the final image, because your eyes will be somewhere here. Okay, and what is the visual angle? Angle formed at eye by the object or the image. Okay, so here will be somewhere, here will be your eyes, and this is the final image, and this final image is forming the angle beta. Okay, and this is the beta is the visual angle formed by the final image. Now visual angle formed by the object, so these are the rays from the object, so you can say this angle will be alpha. So if this angle is alpha,
Yes,
so
sir.
vertically opposite angle, so this angle will also be alpha. Now you can see this image. This image is small, okay, because rays are coming from the infinity and meeting at the focal plane, and this image is very small.
Yes,
This
sir.
image is very small. If and now related to this image, this alpha and beta will also be small angles. Alpha and beta will also be small angles. Why I am saying alpha and beta are small angles? Because you can see the size of this image is small, and this line is passing from this image. So this angle beta will be very small. This alpha will be very small because this height is very small. So you can say that alpha and beta are small angles. If alpha and beta are small angles, then we know one thing in math: tan alpha can be written as alpha, or tan beta can be approximately
Yes, sir.
equal to beta. Tan beta can be approximately equal to beta. Okay.
Beta.
Now, first we will find tan alpha, or first we will find tan alpha. Now, how we will find tan alpha? This is alpha. See in this triangle. This triangle. See, are you getting this triangle? This triangle?
Yes, sir. Yes, sir.
This triangle. See this triangle. So in this triangle, if you want to find tan alpha in a triangle will be perpendicular divided by base.
Yes,
So
sir.
this is the perpendicular. A dash B dash is the perpendicular, and this FO and this distance is the base, and this is
Base.
FO. Okay. So basically tan
Yeah.
alpha will be A dash B dash divided by this distance, and this distance is FO. So tan alpha is equal to A dash B dash divided by FO.
FO.
Now, tan beta, we can find tan beta also. Now see, this angle is beta. Okay, this angle is beta. Now see in this triangle, tan beta can be written as A dash B dash divided by this distance, and this
Yes,
distance
sir.
is UE. This distance is UE. So tan beta is perpendicular divided by base. So perpendicular of this triangle is A dash B dash, and base is UE. So tan beta, you can write A dash B dash divided by UE. Okay, you can also do this derivation very easily, but for that you have to practice. Okay.
Yes, sir.
Okay, tan beta we have. Now we know that tan alpha can be written as alpha. So we can write alpha is equal to A dash B dash divided by FO, and tan beta can be written as beta. So beta will be A dash B dash divided by UE. Now magnification is beta by alpha.
Yes, sir.
So we can find the magnification. What is beta? A dash B dash divided by UE divided by alpha. Alpha is A dash B dash divided by FO. Now A dash B dash will be cancelled out. A dash B dash will be cancelled out. Magnifying power of the telescope will be FO divided by UE. What is FO? FO is the focal length of the objective.
Focal length. Yes, sir.
Focal length of objective. Focal length of objective lens. UE is the object distance for eyepiece lens. Object distance for eyepiece lens. So basically, this is the formula for the magnification of the telescope. Okay, FO divided by UE. Okay. Now we will discuss different cases also for the magnifying power. Okay, we will discuss different cases also for the magnifying power. First, you should draw this diagram properly. Then we will discuss the maximum magnification and when the image will form at infinity. Okay.
Yes, sir.
Okay. First draw this diagram. Okay. Write down this also. Okay. Write down this also. First write down this, then draw this diagram. Ask me to scroll down.
Sir, are you free tomorrow, sir? Can I give extra class?
Actually, I will keep your extra class on Friday. Okay?
On
Because,
Friday?
on Friday, because tomorrow I am having
Sir, in the
already.
morning, sir, not in the evening, in the morning.
That is what I'm telling. Actually, tomorrow I am having the classes of 5 hours already.
Oh, okay. That's fine, sir. Leave it.
Yeah, yeah. So actually, so that is why I am keeping your extra class on Friday this time.
No, sir, because next week our practical will start. So,
Okay. From the next week,
yeah, like next Monday.
from the Monday.
Yeah.
So you will be regular during that, or
It depends, sir. What's my next practical?
okay. Okay, so on Friday, mm, actually, tomorrow I'm having a classes of 1, 2, 3, 5 hour 30 minutes of classes already. I am having.
Okay, so it's fine. It's fine. It's too much of classes.
Yeah.
Done, sir.
Okay, so this will be okay. This also you have to do. Okay, write down this also. Then we will discuss.
Done, sir.
Okay. So now we will discuss the cases for the magnification, maximum magnification. So in case of the maximum magnification in the telescope, so if you want the maximum magnification, then final image will formed at a distance of d, means at a distance of 25 centimeter. Means this final image in case of the maximum magnification will be at a distance of 25 centimeter. That is capital D. Capital D is what? Capital D is what? 25 centimeter, least distance of distinct vision. Least distance of distinct vision. Okay, so now here the final image is forming uh, at the 25 centimeter. So we can calculate the magnification from here. Okay, so final image is forming at a distance of d. So the position of image we can take minus d, because this image will be in the here, and when you will with respect to the eyepiece, the image distance, because final image is formed by the eyepiece. Okay, final image is formed by the eyepiece. So with respect to the eyepiece, we will take the image distance. So image
Yes,
distance will
sir.
be taken as negative. Why negative? Because the incident light is in this direction. Okay, so v, that is why I have taken as negative. V is equal to minus d. After that, u will be minus ue. Okay, u will be this distance with respect to the eyepiece lens. Ue will be minus ue, because you will measure the distance in this direction and incident light is in this direction. Okay, so u will be minus ue, and focal length will be the focal length of the eyepiece. F will be focal length of the eyepiece lens. Okay, so now we can apply the lens formula, that is 1 upon v minus 1 upon u is equal to 1 upon f. Okay, 1 upon v means 1 upon minus d minus 1 upon minus ue is equal to 1 upon fe. So from here you will get 1 upon ue. This minus minus become plus, so it will become 1 upon ue. This is 1 upon minus d. Okay, minus 1 by d, it will go here, it will become plus 1 by d. So it will be 1 upon ue is equal to 1 upon fe plus 1 upon d. Okay. Now, what is the formula of the magnification? Magnification is focal length of the objective lens divided by UE. Okay.
Yes, sir.
Now it will be FO and U 1 upon UE. This is 1 upon UE. 1 upon UE is this value 1 upon FE plus 1 upon FE plus 1 by D. So from this equation, when you will take FE common, so you will have the magnification this FO by FE, FO by FE, it will be 1 plus FE divided by D. So this will be the case of the maximum magnification.
Yes, sir.
Now second case, normal adjustment. In case of the normal adjustment, the final image will form at infinity. Final image by eyepiece at infinity. Means final image will be at infinity. Object distance will be again minus UE and focal length will be again focal length of eyepiece. So here we can apply the length formula, that is 1 by V minus 1 by U is equal to 1 by F. 1 by V means 1 by infinity minus 1 upon minus UE is equal to 1 upon FE. It will be 1 upon FE. Why this is not? Just a minute. It will be 1 upon FE. Now from here, we know that 1 upon infinity is equal to 0. Okay, 1 upon infinity is equal to 0. So you will have minus minus plus, it will be 1 upon UE, 1 upon UE and is equal to 1 by FE. So you will have 1 upon UE is equal to 1 by FE. Or you can write UE, you will get FE. Now magnification of telescope is focal length of the objective lens divided by UE.
Yes, sir.
So you will get the magnification M, that is equal to FO. Instead of UE, you can write FE. So this magnification you will have. The value of magnification you will have this.
Yes, sir.
Okay. Now there is one more term, length of the telescope. There is one more term, length of telescope. Length of telescope, that is L. So in this case, the length of the telescope will be the length, will be the distance between the objective lens and eyepiece lens. What is the distance between the objective lens and eyepiece lens? FO plus UE. FO plus UE. Okay, so you can take in terms of mod FO plus UE. Why I am taking mod? Because distance is always positive. Mod, in mod, I told you the value will remain always positive. Okay. Now in this case, if you want to find the length of the telescope, that is equal to L. What is the length of telescope? We know FO plus UE mod.
Yes, sir.
Now in this case, what is the value of UE? UE is equal to FE. So you can put length of the telescope in this case FO plus FE. So this will be the length of telescope. We can, Harsh, we can put your extra classes on continuously on the Friday, Saturday, Sunday. Means it then will be Friday, Saturday, Sunday. Okay, I will see. Actually, tomorrow it will be not possible, and day after tomorrow also. Day after tomorrow is your class with me. Okay. But tomorrow the extra class is not possible because I already have so much of classes. So you
Yeah,
can
it's
understand that.
fine.
But we can put the extra other classes at the Sunday and Friday if you will be free then. Okay. So first write down this.
So Sunday, I don't think I'll be free. Friday, I'll be free.
Why on Sunday? What in Sundays will be your
Sir, I told you that I have to study for practicals. Have a
okay,
moment.
fine, fine, fine. Okay, fine. Okay, write down. Then we will discuss numerical, and after that we will discuss reflecting telescope.
So, student.
Okay, write down this fast, then go to this.
Done, sir.
Done. Okay. Harsh, do you know about Al Nasr?
So, can you
It is
repeat?
that is a football
Yeah,
group.
it's in Riyadh. It's in Riyadh. I know that.
It's in Riyadh or in Saudi?
Yeah, it's in Saudi, like Riyadh.
So
It's
Saudi, na Ronaldo now
yeah,
Ronaldo is a part of that. I think
yeah.
that is of Saudi. You are in Saudi now?
Yeah, I'm in, but I'm 4 hours away from Riyadh.
Okay, okay.
Let's scroll down.
Yeah.
Done, sir.
Okay. So now we will see the summary. There is no need to write this summary because already there all the things. Now in summary we have the magnification of telescope is equal to focal length of the objective lens divided by the object distance for the eyepiece lens. So if this
Yes, sir.
magnification is the maximum, if the magnification
Yes,
is
sir.
maximum, what was the condition? Image is found by the eyepiece at D, and you will get the formula of the magnification. This m is equal to
Yeah.
fo by fe 1 plus fe by d, and length of the telescope in this case fo plus ue. Now in case of the normal adjustment, final image will form at infinity. And what is the formula you will get finally
Yes, sir.
of magnification? Fo by fe, and length of the telescope in this case will be fo plus fe. Okay, so this summary I'm copying because there will be requirement of the formulas. So we'll solve the numericals now. Okay, so already there summary. So now this see this numerical. So in this numerical, they are saying a refracting telescope is under normal adjustment. There is a refracting telescope is
Yeah.
that is under normal adjustment, and its magnifying power is 5 if the length of the telescope under this condition is 150 centimeter when final image is formed at infinity. Okay, we know that under normal
Infinity.
adjustment, we know that under normal adjustment, you can see under normal adjustment where the image is formed, final image is at infinity. So it is given in the question under normal adjustment, final image at infinity.
Yes,
Mean
sir.
all the formulas we will use these formulas. Okay, because this is the case of the normal adjustment
Yes,
actually.
sir.
So for the normal adjustment, we have these formulas. We will use these formulas. Okay. So this is very easy question. So magnifying power is 5. Means M, capital M is given. Capital M is 5 given, and what is
Yes,
the
sir.
formula of the capital M? FO by FE. Okay, it is FO by FE.
FO by FE.
FO divided by FE. So we will get FO divided by FE is equal to 5. From here we can find FO, that is equal to 5 times of FE. So suppose this is equation
Yes,
number
sir.
1. Now another thing is the length of the telescope is 150 centimeter given. Length of the telescope. Now what is the length of the telescope in case of the normal adjustment? FO plus FE.
FO plus FE.
Yeah. So length of the telescope is given as 150 centimeter. So length of telescope is FO plus FE, and that is equal to
Yes.
150 centimeter. Now you can put the value of FO. FO is 5 times of FE.
5 times FE.
Yeah. So basically,
So it will
I
be
want,
6 FE.
yeah, it will be
And then
6
if
FE
it comes to
divided by
6,
150. Yeah.
yeah, so
FO, it
150
will be,
divided by
yeah.
6, it will be,
It will be 5 FE plus FE is equal to 150. So you will get 6
yeah,
FE is equal to 150. So
yeah.
FE you will get 150 by 6, and when you will divide it by 6 you will get 25 centimeter.
Yes, sir.
Now from here you can find FO. FO is 5 times of FE. So it will be 5 times of 25. It will be 125 centimeter. It will be 125
125 centimeter.
yeah. Okay. So basically in this way you have to solve the questions. In this way
Okay, sir.
you have to solve the question. Now another question I am taking. Another question. We can take one more question. So this question, in this question it is given that focal length of the objective lens of refracting telescope. There is a refracting telescope. There is a refracting telescope. In that refracting telescope, the focal length of the objective lens is 100 centimeter, and that of eyepiece lens is 5
Eyepiece is
centimeter.
5 centimeter. 5
So
centimeter.
focal length of objective is 100 centimeter, and focal length of the eyepiece is 5 centimeter given. If the final image is formed at least distance of the distinct vision, means this is the case. Image is forming at D. Okay?
Yes, sir.
Least
Yes, sir.
distance of the distinct vision, that is D. So it is a case of the maximum magnification. So all the formulas that we will apply is this. Okay? So these formulas we will apply. This formula. Find magnifying power and the length of the telescope. We have to find the magnifying power and the length of the telescope. Now you can see the formula for the magnifying power is this.
Yes, sir.
So we can apply this formula. M is equal to FO by FE1 plus FE by D. All the values we have. We have all the values. So M is equal to focal length of the objective lens 100, focal length of the
Yes, sir.
eyepiece lens 5, 1 plus focal length of the eyepiece lens, that is 5, and D is 25 centimeter. Okay, so when you will solve it, it will be 20, and it will be 5 5s are 25, it will be 5 1 6 by 5, so it will be 5 4s are 24, 5 4s are 20, so it will be 6 4s are 24. So magnifying power will be 24. Okay, magnifying power of the telescope you will get 24. Why you are applying this formula? Because this is a case of the maximum magnification, because this is given final image is formed at the least distance of the distinct vision.
Yes, sir.
Okay. Yeah, now we have to find the length of the telescope. Length of the telescope is this, FO plus UE. Now we have FO but we do not have UE. We have FO but we do not have UE. Now we can find UE. It is given that the final image is forming at D.
Yes, sir.
So final image is forming at 25 centimeter, means the position of the image we can take 25 centimeter. Focal length of the eyepiece lens is given as 5 centimeter. So we can find UE. Okay, U is equal to UE. We have done this already. So we can apply 1 upon V minus 1 upon U is equal to 1 upon F. 1 upon V means 1 upon minus 1 upon 25. It will be 1 upon minus 25 minus 1 upon U is minus UE is equal to, this is U suffix E. U suffix E is equal to 1 upon 5. So you will have 1 upon UE is equal to 1 upon 5 plus 1 upon 25. So you can take 25 LCM. So you will have
Yes.
5 5s are 25
5 5
plus
6
1.
6.
Yeah, 6. So
6 by
UE you will
25.
have 25 by 6. So the answer will be, it will be 6 4 24,
4 24. 4
and it
point
will be 1
1.
4.116. It will be
Yes, sir.
166 centimeter.
Yes.
So now you have UE. Now if you have FO and you have UE, you can find the length of the telescope. Length of the telescope is FO plus UE, and FO is 100, UE is 4.166. So you will have 104.166
6.
centimeter.
6.
So in this way you can find the okay. So this is the answer of this question. Okay, first write down fast.
Second scroll down. Second scroll down. seconds ಕೂಡ. Done, sir.
This is the refracting telescope. Well, now we'll discuss the reflecting telescope. And why there is a requirement of refracting telescope? Because in case of the refracting telescope, we have the objective of large aperture. You can see here. This is objective. This objective is very large as compared to the eyepiece lens. So for the manufacturing of this objective lens, okay, there are some difficulties. Okay, so the problems associated with large objective lens are: number one, it is difficult to manufacture. Difficult to manufacture. Number second, it is costly also, because you are making large large objective, so it will be costly also, because the material will be costly.
Yes, sir.
Yeah, and difficult to held mechanically. Okay, to hold that length of large aperture is also difficult. Okay,
Yes, sir.
so difficult to be held mechanically. Held mechanically. And there are two more problems. One is spherical aberration. Spherical aberration means if you have a suppose a lens. If you have a lens, they can ask in board also, for example, what is spherical aberration. So if this is a lens and sorry, this is a lens, and if this is the principal axis, now we know that this object, this is the objective lens we are taking, and this is objective lens is of large. Objective lens is large. Okay, this objective lens is large.
Yes, sir.
So if this objective lens is large, but what we have studied till now, we have assumed the aperture of the lens very small. Till now we have discussed that. We were discussing the aperture of the lens in our syllabus is very small, but in case of the telescope,
Yes.
we are using the lens of large aperture. So due to that large aperture, there is a problem, spherical aberration. Now I am telling what is spherical aberration. There are two types of rays. One is paraxial rays. Paraxial rays are the rays which are very close to principal axis. like this, very close to principal axis. So these are the para-axial rays.
Yes, sir.
Now there are other rays, marginal rays, which are far from the principal axis, which are far from the principal axis.
Yes,
And
sir.
this lens has the large aperture, so these rays, these green color rays, will be very, very far from the principal axis. So there is a problem. What is the problem? These paraxial rays will have different focus, meet at some different point. Okay, and these marginal rays will meet at different focus. Means these marginal rays will meet here. So this is the focus of paraxial rays. This is the focus of marginal rays. These are the
Yes,
marginal
sir.
rays. Marginal rays. So now there are two focuses, and if there are two focuses, so uh, and why this is happening? Because if there are two focuses, means rays are parallel. So these
Yes,
rays
sir.
will not meet at a single point. These rays will meet at different points. So there will be the effect on the image. Image will not be clear image. You will not get the clear image. So actually, why this is happening? Why the spherical aberration is happening due to the shape, due to shape. And this if spherical aberration occurs in lens plus mirror, both. This spherical aberration you will get in lens also, in mirrors also. And why this is the spherical aberration is taking place? Due to the large aperture. Now there is one more problem, that is known as the chromatic aberration. Chromatic aberration. In case of the large aperture lens, there is one more problem, that is chromatic aberration. And this chromatic aberration is due to the different colors of light. Okay, and this happens only in lens, not in mirror.
Yes, sir.
Only in lens, not in mirror. Okay, now we know that VibGyor, VibGyor. So if you are moving from violet light to the red light, then the wavelength will increase. Lambda is the wavelength, and wavelength will increase. Refractive index of the lens is inversely proportional to the wavelength. Okay, refractive index of the lens is inversely proportional to the wavelength we discussed. What is mu? Mu is the refractive index
Yes.
of the lens. Yeah. So if you have if you have this lens, if you have this lens, and rays are coming, we know that white light is made up of 7 colors.
Yes, sir. With cure.
Yeah, Vibgyor. So actually, what happen? Uh, different color will refract differently. If you are taking a red color, okay. If you are taking a red color, so the focal length of the red color will be means the focus of the means the red color light after refraction will meet here.
Yes, sir.
Just a minute. It will be red. This will be the focus of the red color, and for the violet color, if this is a violet color here, so this color for this color, the converging will be different. Somewhere here will be minimum. So this violet color will meet here. This is red. This is the red color, and this is something like violet color. So basically, different color will in different colors, the refraction will take differently. So color will get separate out. So we will get different colors images. Okay, we will not get
Yes, sir.
proper image. We will get the different color images, and that is not good. So this is the problem with the chromatic aberration. Okay,
Yes, sir.
chromatic aberration. So you can now write down.
So you can scroll down.
Here.
Second school.
Yeah. So we can add one point here. Different colors will have different amount of refraction. Different amount of refraction due to different wavelengths. Due to different wavelengths.
Done, sir.
Write down this statement also.
Sir, I wrote that, sir.
Okay. So why this is happening? Why different colors have different refraction? Because this lens have some material,
Yes, sir.
and that material will have the refractive index mu, and
Okay.
that refractive index is inversely proportional to the
Proportional to
wavelength.
1 by, yeah, 1 by
Uh,
lambda.
and there is one formula we studied, lens maker formula. Focal length of the lens is mu minus 1, 1
Yes.
upon R1 minus 1 upon
Minus
R2.
1 R2.
Now you can see, you can see this mu from here. See the relation. Mu is inversely proportional to lambda. So you can
Yeah.
say, indirectly you can say the focal length will be inversely proportional to lambda.
Yes, sir.
Okay, focal length will be inversely proportional to lambda. Oh, sorry, this is not f. Basically it was 1 by f. So if it is 1 by f and here is mu, and this mu is depending upon 1 by lambda, so you can say that focal length is directly proportional to somehow to the wavelength. Means what does it mean? So focal length is directly proportional to wavelength. It means that the color have the maximum wavelength. Okay, the color have the more wavelength. More will be the focal length like this. So for red color, the focal length will be more, and for the
Yes,
violet
sir.
color, the focal length will be less. Why the focal length will be
Yes, sir.
less? Because the
The wavelength
violet current have
is,
a least lambda. Okay, it will
yeah,
have
least lambda.
more value of lambda. Lambda means the wavelength. It will have
Wavelength.
least lambda. Okay, so please copy this formula also, because from this formula I have made a relation this.